I know we don't love word problems. No kid really ever does. The good news is, remember, it's formulas. You will be provided the formulas on the test. You just have to know how to plug the numbers in and get the equation solved for. So of course today we're going to be looking at several different types of formulas, and we're going to be using logarithms, maybe exponential, to get some of these equations solved. Okay, here is our first one of the day. So exponential growth, we're talking about doubling in time. Now, when I say you'll get the equations, you'll get that. You need to know, of course, what all those different variables mean in the equation. Anytime, just to try to save some memorizing, anytime you see the subscript 0, n sub 0, that is your initial or your starting amount. Because you're going to see that, the sub 0, in some other formulas. So that is your starting amount for the record. Okay, doubling time. Well, the 2's there because of the double. That's pretty exciting stuff, I know. Doubling time is A, size of the population at time t is given by that equation. And of course, notice A and t have to be in the same units. Whether it's minutes, hours, days, years, whatever, just make sure that the time measurements are the same. No mixing and matching. I know it's very dramatic, I promise you it's very easy. All right, here we go. Under ideal conditions, a certain bacteria population doubles, so I'm using that formula, every 3 hours. So I need this little nugget of information, and they tell you there's initially 1,000 bacteria. Find a model, so an equation, for the bacteria population after t hours. So, as I click it back, of course this is my layout or my formula I'm going to be using. So I'm going to reread it. The initial quantity goes in for n sub 0, the 2 stays as 2, and then we're going to figure out what's t and what's a. So here we go. So n, got a t. So of course my initial amount is the 1,000, what you're starting with. Now I'm going to put the times the dot sign in just because I don't want this to look weird here. I want it kind of separate from the 2, so I'm going to put that in. Now you're solving for the t over a. A is the how long it takes to double, which in our case it takes 3 hours to double. So there is our model. Now, next quick question for you. Can you multiply the 1,000 and the 2 together? We've talked about it. No, you would be breaking order of operations. I'm done. That's my model. I'm done with A, I should say. B, how many bacteria after 15 hours? So I'm going to take my model and replace t with 15. Okay. And just to make it look fancy, I'm going to put the 15 in for t here on this side. I'm putting 15 in for the variable. Now I can't really say I would leave that 15 over 30. I'd just make it 5. So I know you can punch that in your calculator. I'm not going to bore you. You type it in. You get 32,000. And again, when I typed it in, I literally 1,000 times 2 to the 5th power. Okay. All right, here's where it gets fun, because we got to do a little more work. How many hours will it take the bacteria count to reach 100,000? So how many hours? So we're solving for t. We have to figure that out. And we're going to end up with 100,000 bacteria. Sounds weird and gross. Okay, so we're going to, this time, I know, bacteria, I don't know why it always weirds me out, problems with bacteria. So we're going to equal 100,000. We still start with the 1,000. We still have the times 2 in our formula. You're solving for the t, and we're, of course, over 3. So this is the problem, the one that really counts, because here we have to use some of our logarithm skills, exponential skills, etc. Now, whenever you're like, oh my gosh, I don't know where to start, old school algebra 1, I'm going to try to get the variable alone. So I'm going to divide off 1,000. Okay, 100,000 divided by 1,000 is 100. Yeah, we need a calculator for that, right? Okay, you have an exponential equation here. You have choices, okay? I could try to figure out is 100 2 to some power and make common bases. I don't know if I really have that in me, plus we can use our calculators. So you're in exponential form. Let's just convert it to log form and punch it in our calculator and make it easy. So I'm going to move up here because I'm at the bottom of the board. So I'm going to be log base 2 of what? 100 equals our exponent t over 3. So of course that, you know how to type that in your math menu, letter A, and then of course to get t by itself, we're going to have to times each side by 3 to clear out that fraction. All right, type that all in. It doesn't say what to round to. For the thrill of knowledge, I rounded to the 10th if you want to do the same. Half the battle's typing it incorrect. All right. What do you got for it? Somebody, anybody?
19.9.
I agree. And it's a word problem. I feel the desire I should label it.
Hours.
We're finding time. We're in hours. Okay. So I think for word problems, these really aren't bad because you're really just plugging the numbers into the formulas, which you will be provided. So you can't beat it. Okay, certain breed, by the way, I don't make up these problems. I just don't know the book because certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island, I can't read today, is estimated to be 400 and doubling every 3 months. So I got some key numbers here. Of course, our 4,100. What was the initial size of the rabbit population introduced to the island? Okay, so initial size of the rabbit population. So we are solving in our formula for that n sub 0. So I'm thinking about all the other things to fill in. We've got the times 2 to the t over a. Now, careful here. I'm going to put the little fraction mark in. Obviously, our time values are 8 months and 3 months. Which goes where? Is 8 on the top or 3 on the top? Remember, the a, the bottom, the a, is how long the time it takes to double. So I'm reading that closely. They double every 3 months. So the 3 is the denominator on your fraction. And, okay, right now, our current I cannot talk today. Our current rabbit population is the 4,100. It's because I'm so mad at geometry. They can't even plot points today. I was about to rage on them. But anyway, I'm going to get over it, kids. So to get your n sub 0, we're just going to divide off your 2 to the 8/3. And you're just going to big calculator problem. Punch that in and see what you get. Now, let's think about rounding. We're talking about rabbits. So what are you rounding to? I'd go whole number. It seems weird to have point whatever of a rabbit. Seems weird and gross, okay? Thanks. I don't want to go down a rabbit hole. I won my game today, kids. I won my game. All right. Well, how many? Oh, it's cringing up here. How many rabbits do we have? 646 rabbits. I guess I'll label. Okay. Here we go. Estimate the population 1 year after the rabbits were induced into the island. Okay, so I'm using my formula. Of course, we now know our initial amount of rabbits times 2. Now, we know, of course, the 3 months to double. Little trickster here, my friends. 1 year. I need the same time measurement units. This is months. You're in a year. How many months in a year? 12. So we have to make that 12. So just catch the converting, of course. Okay, punch that in. And again, we're talking rabbits. I'd round to the whole. I hear 10,000. What do you got? 336.
Oh my gosh.
All right, any questions on that one? I just love the oh my gosh, Owen. I don't know, it makes me giggle. Ready for the next formula. And again, don't forget, you'll always be given the formulas.
Do we get the title of the formula?
It'll be in the problem even.
It'll be in the problem?
Yep.
So like, we'll get it and we'll know that it's the exponential growth. that
Right,
one
like
time?
you'll get, like it'll have the problem and then it'll have in italics the formula right
What
under
is your
it.
problem? Thank you.
Because there's some things that, there's certain formulas I think as mathematicians we should have memorized, like quadratic formula, Pythagorean theorem, certain big formulas. But some of these, let's be honest, it's a technology age, you could look up the formula. I want to make sure you know how to use it and solve it.
I see.
Okay, that's how I roll. All right, exponential growth. Here
Stop
we go.
looking at me, Owen.
Oh my God. Oh my God. Okay, population experiences exponential growth. Here's our formula. Now, and like I said, you will see a pattern in a lot of these formulas. N sub 0, of course, is your initial population. That's always the starting, whether you're talking about bacteria doubling or whatever. Population, the sub 0 is the starting. E is your E on the calculator. R, rate, T, time. Okay? Seems pretty self-explanatory. So here we go. So the initial why do I keep doing bacteria problems? I'm really regretting this. The initial bacterium count in a culture is 500. Biologist later makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. Find a function that models the number of bacteria after T hours. So you're just setting up the formula. That's all we're going to do. So N of T, our initial amount's the 500, E, and then of course to the RT. Now the rate's the 40%. I don't have a percent key in my graphing calculator, so I'm going to put that as a decimal. I don't care if you have the 0 or not. I just threw it on there because it looks fancy. And then of course, time. So when it just asks for the model, it's just asking you to set it up because clearly we're going to use it for B and C. What's the estimated count after 10 hours? All right, throw 10 in for T and punch it in your calculator. So when we put 10 in for time, E, that's a very sloppy E. Punch that in the old calculator. Here the calculator key is clicking. Bacteria. I rounded to the whole. I don't know. Can you have part of a bacteria? I feel like this is a question for Mrs. Angela. So I'm going to ask her. Okay. So you should add, I went to the whole. 27,300. I guess I'll label bacterial. Got it. Okay. After how many hours, so we are solving for time, will the bacteria reach 80,000? So you know what you're supposed to equal. Our initial amount is still the 500. Our rate's still the 0.4. We're finding the time. So it's usually part C is the one I really care about, obviously, because you have to do a little bit more work to solve for the time. So obviously I'm going to get my variable by itself. I'm going to divide off the 500. So 80,000 divided by 500, punch that in, what's that? What do you got? 160, I heard it. Now, clearly, we're in exponential form. I can't tell you what T is going to be in my head. We're going to convert to log form. But we would be in a log base E. We're past writing log base E. We know log base E is what? ln. So we're going to do the ln of 160 equals the exponent. And then I'm going to divide off the 0.4. All right. Punch that in. Round, I don't know, surprise me, round or whatever.
12.7.
12.7 for the web. So any questions on that guy? 3 down, 2 to go. All right, cruising on. Okay, expressing model in terms of E. A culture, I'm really upset with all these bacteria problems and we're getting it. Culture starts with 10,000 bacteria and then a number doubles every 40 minutes. So Avery, to kind of answer your question like the test, like how I've got the formula here, like it'll be embedded in the question. You'll see on the test like the formulas will be like on the side in each question for you. So you don't even have to try to be like, oh my gosh, which one is that? I care that you can use it. All right, back to it. Culture starts with 10,000. So clearly that's my n sub 0, doubles every 40 minutes. Here we go. Find a function. I'm on it. So 10,000 is our starting amount. times 2. I just like to put the dot in, otherwise I think it looks like 10,000, you know, it looks weird, the number on that. I like to put it in there. And then of course our time. Now, to double is the 40 minutes. Now, I'm like, okay. Hours. We got to do a little converting because they want you to get the model for hours. They told you the time in minutes. Well, 40 minutes is how much of an hour? What fraction? 2/3. So I'm just going to put underneath that's 2/3 of an hour. Which this is going to look a little weirdo. I don't really like it because we're going to have t over 2/3. Okay, I got to do something with that because we generally never leave a fraction within a fraction. We call that a complex fraction. So really what you have in that fraction, I'm going to do a little work over here and try to clean that up. We have t divided by 2/3. Well, we know when we divide a fraction, you multiply by the reciprocal. Oh, okay. Or even, since we can use decimals, what's 3 over 2 is a decimal? 1.5, yeah. So, because I don't want to have that fraction within a fraction, it looks weird. I'm going to clean this up for us. So instead of t over 2/3, I could either put 3/2 t, or I'm even going to go 1.5 t. Let me fill in my n over t. So that was just a little fraction cleanup I had to do there. Otherwise, still pretty much easy. Find a function, and they give you this formula for the number, of course, after t hours. Okay. Oh boy. Okay. Getting crazy over here. Find a function. So let's work on this part of it. So this is where we're at here on this guy. So I'm going to have to do, a little bit of work here. Find a function that models the number of bacteria after t hours. Okay. So we still got our 10,000. RE. Now here's kind of the funzo part. Our rate, and then we've got our time. Well, I don't know the rate, but we already figured out the time was that 2/3 of an hour. Now, we can figure out the final amount over here. Doubles. Here in this formula, they had the 2 already inserted for it. Here I got to do a little bit mental math. If my 10,000 is doubling, you're going to end up with how many? 20,000. So I came up with the 20,000 because of the doubling. That's already offset in this version of the formula. It's not in ours. We need the rate. We're going to figure it out. I'm like, okay, I got this. It looks messy, but I got it. I'm going to divide 10,000 off. I'm going to do that in our head. I just don't like how this looks. I'm going to make it 2/3 R. That's just me being OCD there. Now, of course, I can't figure out R in my head. You're in an exponential form. Let's put it to log. We're not writing log base C anymore. We know it's ln 2 equals our exponent. And I'm like, oh, I can do that all in my calculator. To get R alone, I'm running out of room. We're just going to divide off the 2/3. So figure out what's the ln of 2 divided by 2/3. I don't care what you round to. It doesn't say. Surprise me. What do you got? 1.04. Okay. So my final answer, just because I'm going to make this prettier, says find a function. So I needed the rate so I could do the function. Now I'm just going to write out the formula so it looks all fancy, okay? So n of t, our initial amount doesn't change, the 10,000. E, we now know the rate, and we're finding a function, of course, in terms of time. So this is one of the quote-unquote trickier problems. You're in minutes, they wanted it in hours, so catch that, read close, convert it. And then I came up with the 20,000 over here because it was doubling the 10,000. So you just got to read close, story of our lives. All right, are we ready for the final formulas? Final ones. I feel like I'm teaching science today, for sure. Radioactive decay. Okay, decay, we're decaying. Of course, here the rate of decay is proportional to the mass. Probably, maybe, I don't know, in science class, talk about half-life, the time it takes for the sample to decay to half its original mass. Now, there are 2 different versions of the formulas that you're going to use. Remember, I'm going to give you the formulas. They're really the same, though. Because if you have a negative 2 to the negative 1, really, 2 to the negative 1 is 1/2, okay? And I usually tend to use this version of it because to me, I'm just like, oh, it makes sense. The half-life version has a half in it. A half, I don't know, I just kind of like that in there, but they are the same formula. T, of course, the time, and then the half-life, how many years, months, whatever it takes for it to become half of it and stuff. Again, I'll always give you the formula, so no worry there. Okay, so more formulas for us here. All sorts of good formulas for us. Let's take a look at this one. So radioactive decay. So your initial mass, the half-life, remaining in time T, of course, M sub 0 is your initial amount, R rate, T time. Now the nice thing is here, they also give you a little formula for the rate. ln of 2 divided by the half-life. H stands for the half-life. You'll get all the formulas. You just have to know how to put them together and use them. So let's do it. Polonium-210 has a half-life of 140 days. Suppose a sample of this substance has a mass of 300. So here we go. They give you the formula. Find a function that models, I missed the L there, okay, that models the mass remaining after T days. All right, well, let's figure out the function here. So I just need the formula. Okay, initial amount. Well, read closely. What's your initial amount of the substance? 300. And then I've got my 1/2. And then your exponent, of course, you've got the fraction. Now, it wants you to do it in terms of T. That stays as is. And you can see the half-life of it is 140. So there's my model. I don't have to do anything else. Now, find a function that gives you the formula over here, of course, that models it after T days. All right, let's see what we got. Okay. Initial amount, well, I mean, that doesn't change. That's still your 300. E, negative, that's a baby negative there. I know I've got the T there. I'm like, I need the rate. I need the rate in this. So I'm like, okay, I gotta do a little work here for my rate. So again, rate, look at that. You've got a formula for the rate. The ln of 2 over the half-life. Oh, okay, all right, I can do that. ln of 2 over our half-life of 140. Punch that in your calculator. You can see I gotta look. I clearly don't know what that decimal is off the top of my head. You get negative 0.00495. And if you round that differently, obviously I don't care. That's gonna affect your final answer a little bit, but that's fine. So now I'm gonna come back and put my rate in here. Got it. And I'm gonna pick up T. So a little bit of work to find the rate, but again, you have the formulas. Okay, now we're gonna use these in C and D, obviously, which I couldn't fit all in one slide, so here we go. Find the mass remaining after 1 year. Okay, first question for you. Now, they're scaling this with the previous problem in days. Okay, big deal. How many days are in a year? 365. So that's the first little note I'm gonna make. Okay, I didn't give you the formula, but really we do have it. You have 2 versions of the formula. Does it matter which one you use? No. You can put 365 in the green one. You can put 365 in the blue one. You get the exact same answer. Maybe a smidge difference because I rounded this decimal here, but you'll get the same. So clearly, I don't care. I'm going to set up the green one first. So maybe you did, we're putting in 365. So of course, you've got your 300, your 1/2. Oh, I need longer arms. Our time 365 over your half-life. Or, I don't care, just I'm going to set them up both. You could have done the blue one. You don't have to write both on your homework, obviously. How many zeros was it? 00495. And then your 365. Okay. Either one, again, you might be a little off because I rounded that negative 0.00495, but you'll get the same answer. You should get something close to like 49.3. What are we in? Grams? Milligrams. I didn't label. Shame on me. So it doesn't matter to me which one you use clearly. Okay. Same thing on D. How long will it take for the sample to decay to 200? So I'm just going to click it back a slide. I can use either of these formulas, and of course my final amount's going to be 200. I don't think, I've solved them both. If you look at my little notes, I've solved them both. Honestly, I think probably the blue one might be a little bit easier to use on the solving, just because this is so fractiony. So I'm going to use the blue one. Click over here. So I'm going to have the 200 equals 300 e to our rate, and we're finding the t. You could use the green one, you get the same thing. I've done it both. I just think this is less work, to be honest. I'm going to divide off the 300. So 2/3. You could go 0.67 if you want a decimal there. I'm just going to leave it 2/3 for right now. Of course, I've got to convert now. I'm in exponential. I'm going to put it in log form. Why am I writing log base e? You know it's ln. We said it how many times today? 2/3. All right, you can take it from there. Divide off your decimal, get your final answer. I don't care what you round to, surprise me. You should get about, starts with an 8. I like nobody wants to say it because I don't want to say the wrong thing until I give you the first digit. Green days, yeah. And you do get the same thing if you use the green one and make this 200 and solve and put it to log form. I just think it's a little more time consuming and el yucko because you have more fractions to deal with. So that's why I chose the blue one. But you could use either. You will get the same answer, I promise. Okay, let's talk about tomorrow. That's what everybody's been asking me about. Remember, tomorrow's our favorite, our no graphing calculator quiz. Come on, it's not that bad.
Can we
No.
use a not graphing calculator?
No calculator at all. You don't need a calculator at all, Avery. No. Now, let's remember why I give these to you, not just for my entertainment purposes, although that's a tiny factor.
Really
Factor. Teeny tiny factor, okay? One, to make sure we understand actually how our calculators work and that we can do this without it. Two, when you take the SAT as juniors, there is a no calculator part of the math test. Well, happy tap dance, okay? So some of us are a little calculator dependent, so it's to try to get us a little used to having to maybe do some stuff without it. I literally watched a kid one day in class type in their calculator, -1 divided by 1. Are we a little dependent on our calculators, people? Okay? Okay. So anyway, I'm done with that spiel. What it's going to be? It's going to be 4 problems. 4 problems. There are 3 of the very easy simplifying stuff, like log base 11 of 11 to the 7th.
7.
Bam. Okay? So there's some of those little simplifying easy ones, and then there is one graph on there of a log function. Can you graph a log function in log form? You have to convert it to what? Exponential. Do a little exponents in your head, make your T-chart and graph it, okay? So that's what